All right, now that was great for a single object, but what happens when we have multiple objects interacting with each other, like in the case of a collision? In a moment, we're going to take a look at an example of how to go about looking at conservation of angular momentum when we have collisions. But before we do, I want to make a note about how we calculate the moment of inertia for objects that act like a single object. For example, like two objects after a collision, or one object stacked on top of another one. So to calculate the moment of inertia for a combined object, or an object made up of multiple smaller objects that are all acting like one object, all we have to do is add the moment of inertias of the individual objects. And so, for example, in this image that we have here, I have a red, the person is in red, they're standing on like a spinning disc. So you could think about this like somebody standing on a merry-go-round, okay? Now, the person in the merry-go-round, while they're not moving, right, the person is not moving and the merry-go-round is spinning, they move together like a single object. And so if we wanted to solve for the moment of inertia of the person merry-go-round system, all we'd have to do is add the moment of inertia of the person to the moment of inertia of the merry-go-round, which might look very much like a disc. Now, the person is relatively small in comparison to the merry-go-round, and so sometimes we're going to approximate things as what we're going to call a point mass. So in other words, a point mass is essentially thinking about the person as if they actually had no shape at all. The person is just a single point in space, which is essentially their center of mass. But a point mass is a simplification that we use to solve problems, especially problems involving collisions, when the object itself, the shape of that object, is not as important as the mass of that object and the distance from the center of rotation. And so in this case, we could assume the person is just a single point mass, and we don't need to approximate the shape of the person or worry about how to calculate the moment of inertia of the person. In order to do the moment of inertia for a point mass, it's actually going to look like this. We'll just take the mass of that object and multiply it by d, where d is the distance of that object from the center of rotation. And so again, I want to reiterate that the mass that you see in that equation is the mass of the person, not the mass of the person and the disk, not the mass of the disk, but just the mass of the person or the object that we're treating as a point mass, okay? And d is the distance from the center of rotation. So in the before situation, the person is standing at the outer edge of the disk. And so the distance they have from the center is just equal to the radius of the disk. However, in the after scenario, the person is standing in the middle of the disk, and therefore their distance from the center of rotation would be 0. And so in order to calculate the moment of inertia of this system, right, we could say that the moment of inertia of the system would just be the moment of inertia of the disk plus the moment of inertia of the person, right? We're just going to add them together. Well, that would just be equal to, the moment of inertia for a disk is 1/2 the mass of the disk times the radius of the disk squared, plus, in this case, the mass of the person, so I'll put MP for person, multiplied by d, the distance from the center squared. And in this case, d would equal, we'll use big R here for the radius, because the person is standing some distance, right? If this is their distance, right? Well, then we know that that's also going to be, right? That's also just the radius here, R. That's how far they're standing away. And so we'll use D for their moment of inertia point mass equation, right? That would be the moment of inertia for that system. Now after, right, the moment of inertia of the system would be the same, right? It'd be equal to 1/2 mass of the disk times the radius of the disk squared, plus 1/2 mass of the person times 0 squared, because right here, d equals 0. They're not any distance away from the center of rotation. And so you'll notice that the moment of inertia of the person completely goes away. And all we are left with is the moment of inertia of the disk. And so if you stand at the exact center of rotation, then that person is actually not influencing the moment of inertia of that disk at all. Essentially, it's all just the disk. And so this is how we could go about calculating the moment of inertia for combined objects. And we'll see that come up in the next example.